I was just thinking, you can have a structure built out of Lego, and we call each one of those individual Lego pieces a brick. And you can have a jar of sugar, and we can call each one of those individual pieces of sugar a grain. And we just talked about ionic compounds, and we talked about those things as formula units, which is probably something you haven't talked all that much about before. And if we think about water, and dissolving the salt in the water, and how the salt can disrupt the attractive forces between the water molecules, why is it that we call a salt particle a formula unit and water a molecule? Well, if we take a look at our salt over here, what we can see is that there is a repeating pattern of sodium ions and chloride ions. That is, its 1-to-1 ratio. Whereas with our water molecule over here, we can see that we have 1 oxygen for every 2 hydrogen. That is, that specific oxygen is associated with those hydrogens. Whereas with the chlorines and the sodiums, we can see that they're just sort of interspersed, and they're not actually related in any 1-to-1 ratio aside from the total number of sodium to the total number of chlorine. But more than that, we have a substance that's ionically bonded due to the electrostatic attraction between oppositely charged particles, that is our salt, and we have a structure over here in which there are no ions present. That is, the bonding that exists between the oxygen and the hydrogen is different. The electrons are shared, not transferred, and we refer to this as a covalently bound molecule and this as an ionically bound crystal lattice, and ultimately we refer to the 1-to-1 ratio as a formula unit. So let's review covalent bonding by taking a look at our periodic table. Now remember, our periodic table is split into 2 sides. We have the metals on the left and the nonmetals on the right. Now quite often we'll see hydrogen on the left side of the periodic table over with the metals, but it's probably more accurately, at least in terms of bonding, found on the right side of the periodic table. Now it's important to remember that ionic bonds form between metals and nonmetals, while our covalently bonded compounds, or what we're going to come to call molecules, are formed from 2 or more nonmetals. So if we take a look at a simple molecule of hydrogen gas in which one hydrogen bonds to another hydrogen, in order for these hydrogens to become stable, and remember, when we're dealing with stability, we are talking about getting an electron configuration like that of the nearest noble gas. Now for hydrogen, that nearest noble gas is going to be helium. It only needs 2 electrons. Since each hydrogen has 1 valence electron, it is going to obtain another valence electron from that additional hydrogen. So the hydrogens are actually going to share their 1 valence electron, and so each hydrogen now satisfies the principle that it's going to become isoelectronic or have the same electron configuration as the nearest noble gas, and so we have something now that has 2 valence electrons, and that shared valence electrons, those are what form the covalent bond. So in some of these more complex molecules, there are a series of steps that you're going to go through to make the whole process a lot easier on yourself. So let's take a look at an example and work through these steps, and hopefully by the end of this you'll have a pretty good idea as to how to go through drawing these Lewis structures for the more complex molecular compounds that you might come across. Now the ones that we're going to take a look at, they're only going to have 1 central atom for the time being, but these rules can ultimately be extended to those that have more than 1 central atom. The example we're going to take a look at is carbon tetrachloride. And the first thing that you're going to do is select which one of the elements is going to be your central element, that is the one in the center, and which one's going to be the peripheral element, or the ones that are going to go around the periphery or the outside. Now, the one that goes in the center is the one that we say has the highest bonding capacity of those elements. We should also note that hydrogen is never the central element, nor is fluorine. So in our particular example, carbon has the highest bonding capacity at 4, chlorine has a bonding capacity of 1, so carbon is going to go in the middle. Incidentally, the formula usually also gives it away, so if we have carbon and 4 chlorine, it's a pretty safe bet that you're going to have 1 carbon in the middle surrounded by 4 chlorine. Your next step is to identify the number of valence electrons that each one of these each one of these atoms has. And so since we recognize that carbon is in group 4, carbon is going to have 4 valence electrons. The chlorine, being in group 7, is going to have 7 valence electrons, and because there are 4 of those, the total number of electrons that chlorine are going to bring are 28. Carbon is going to bring 4, so we have a total of 32 valence electrons that we can assign to these elements. And so the first thing that we're going to do is we are going to create or represent the bonds that exist between the central element and the peripheral element. And what you have to understand is that each one of these bonds represents 2 electrons. So each one of these lines represents a shared pair of electrons, or 2 electrons, that we are going to illustrate as being drawn in. We can see that once we've done that, because there are 4 bonds, each requiring 2 electrons, that is 8 electrons that we have now accounted for, and so we have to remove those 8 electrons from our count, which leaves us with 24. The next thing that we're going to do is we are going to take the remaining electrons so as to satisfy the octet rule. And really the octet rule is just giving us a means to calculate the number of electrons that should be around a given element to make it isoelectronic with the nearest noble gas. That is, most of these elements are going to become stable when they have 8 or an octet of electrons around them. So the carbon, you'll notice, already has 8 around it. It has 2, 4, 6, 8 electrons around it because of those 4 bonds. Each chlorine now only has 2 electrons associated with it from the bond, so we are going to add electrons around each of the chlorines until they're all gone, or until each of the chlorines have a full octet. So in this case, once we have the full octet, now we have each of the chlorines having 8 electrons around them. There are 2 in the bond, and then 8 total. 6 are non-bonded, so each of the chlorines now obey the octet rule. The carbon obeys the octet rule. All of them are stable, and that's how we would draw carbon tetrachloride in terms of a Lewis structure. Now, we can come into some scenarios where Lewis structures don't appear to obey the octet rule, and they appear to be a little trickier than they might be in our initial example. So a couple of questions come up. What happens if I don't have enough electrons? That is, what would happen if I get to the end of my structure and I still find that some of my peripheral atoms don't have enough electrons? Well, what we have to do in that case is we have to create a multiple bond. It could be a double bond, it might even be a triple bond, and what you have to do is take one of the lone electron pairs from one of the peripheral atoms and move them into a structure that is going to have a double bond. And so we say that if there aren't enough electrons, you have to have a multiple bond. So why don't you try this out? Try drawing the Lewis structure for nitrogen gas, and I think you'll find that as you're going through the steps, you're going to have a multiple bond in order to illustrate the structure of nitrogen gas properly. Another scenario that comes up was, what happens if I'm trying to draw the Lewis structure of a polyatomic ion? Well, if you are trying to draw a polyatomic ion, and really any ion, you're going to have to put square brackets around it to indicate that this overall particle is charged. And so you have to indicate the total number of electrons, and keep in mind, if it's negatively charged, you're going to have to assign more electrons to it. So if it's a -1 charge, you will have to add 1 additional electron to your total electron count so that you can portion out that electron around your structure. If it's a 2 negative ion, let's say a sulfate or a carbonate, you're going to have to add 2 electrons to your initial count and try and draw it out. If it's a positively charged cation, like the ammonium ion, you're going to have 1 less electron in your total electron count, because a positively charged ion has 1 less electron than it does protons. So you're going to have to subtract that from your overall structure. And again, you can try this out by looking at the carbonate ion and see if you can come up with the appropriate structure. Well, back to our original question. Why can't we refer to sodium chloride as a molecule? Well, ultimately it has to do with the bonding that exists within that particular structure. Within sodium chloride, we have a chloride ion, a negatively charged chloride ion, and a positively charged sodium ion, and it's the opposite charges that create that attraction. And that attraction is what we refer to as an ionic bond. And ionic bonds form ionic compounds. And these ionic compounds are not classified as molecules, because molecules are a result of covalent bonds that exist between a sharing of electrons of 2 atoms, an overlapping of orbitals, and it's that sharing and overlapping that we refer to as a covalent bond, which are characteristic of molecules. So the reason that we can't call table salt a molecule really has to do with its general structure and the way that it forms in general. So hopefully this vodcast has helped you distinguish between ionically bonded ionic compounds and covalently bonded molecules, and why we call table salt a formula unit rather than a molecule. But also, hopefully you have an idea now as to how we approach Lewis structures for molecular compounds. And I really encourage you to practice drawing a few of these, because the more that you practice, the better at it you're going to become and the easier those structures are going to be. Thanks for watching.